This research paper presents a novel method for modeling the power generation of a fleet of photovoltaic (PV) systems, leveraging smooth periodic Gaussian copula and Gaussianization techniques. The proposed approach aims to estimate the joint probability distribution of the power outputs from a large number of PV systems, capturing correlations across individual systems and time. By applying a series of nonlinear transformations, the method maps the power output data to independent and identically distributed standard normal variables, enabling various applications such as synthetic data generation, data imputation, anomaly detection, and forecasting. The authors introduce copula models and Gaussianization as the foundation for their proposed method, highlighting the importance of these statistical tools in PV data analysis. The method involves developing a novel set of nonlinear marginal transforms that map the power from each system to a scalar Gaussian, followed by linear transformations to model the marginally transformed data as a large joint Gaussian distribution. This approach allows for handling thousands of systems simultaneously while remaining robust to real-world data challenges, such as missing data. The paper also discusses the limitations and assumptions of the proposed method, as well as potential avenues for future work. Overall, the research presents a significant advancement in modeling the joint behavior of a fleet of PV systems, providing a comprehensive framework for understanding and predicting their power generation patterns. The research paper introduces a novel method for fitting photovoltaic (PV) fleet data to a smooth 24-hour periodic stochastic process. This approach involves a sequence of 3 invertible transformations, which transform the data into a standard Gaussian distribution. The first step entails a smooth periodic nonlinear transformation to make the data marginally Gaussian, followed by an autoregressive model to account for time dependencies, and finally, a smooth periodic Gaussian distribution is fitted to the residual. The method is demonstrated using PV system data from SunPower Corporation, showcasing different power profiles for systems located in Southern California. The dataset includes 15-minute average power values for 6 systems over a period of 3 months, with the last 2 weeks used as a test set. The authors highlight the efficiency of their method in capturing similarity of power profiles for nearby systems and its ability to handle missing values. This novel approach has significant implications for understanding and predicting the performance of PV systems, providing insights into their operational efficiency and potential improvements. The paper introduces a novel method for modeling and forecasting periodic time series data, particularly focusing on solar panel power output. This approach involves 2 primary steps: marginal transforms and residual fitting. Initially, continuous increasing functions phi-t are sought to transform the original data into an approximately Gaussian distribution for each component. These transformations are periodic and smooth, allowing for dynamic changes over time. Quantile regression is used to estimate quantiles from the data, utilizing the pinball loss function to find optimal solutions. In the second step, a marginal transform AR model is fitted to the residuals of the transformed data. This process involves a convex optimization problem that minimizes the sum of a loss function and a smoothing regularizer term, subject to certain constraints. The variables in this optimization problem include the coefficients of the AR model and the smoothing parameter lambda, which can be chosen automatically using cross-validation. The proposed method is demonstrated through its application to solar panel power output data, showcasing its ability to capture periodicity and non-stationarity in the data. The results indicate that the method provides accurate forecasts and effectively handles missing data. Overall, this research presents a new approach for modeling and forecasting time series data with periodic and non-stationary components, offering potential improvements in various fields such as renewable energy and climate science. Modeling and analyzing time series data with periodic patterns requires a structured approach to account for temporal dependencies and non-Gaussian distributions. To achieve this, the methodology begins by applying a quantile transformation to the data, rendering it marginally Gaussian. This transformation enables the fitting of a vector autoregressive model to the transformed data, which effectively captures temporal dependencies. The residuals from the AR model are then modeled as smooth and periodic Gaussian distributions, facilitating various statistical operations. These operations include sampling, density evaluation, conditional quantile estimation, imputation, and anomaly detection. The proposed model-specific structure allows for efficient performance of these operations using linear algebra. This is particularly advantageous for large datasets, where computational efficiency is crucial. By modeling residuals as smooth and periodic Gaussian distributions, the approach can effectively capture subtle patterns and anomalies in the data. The use of linear algebra enables fast and scalable computation, making the methodology suitable for real-world applications involving large-scale time series data. Overall, this approach provides a powerful framework for modeling and analyzing time series data with periodic patterns, allowing for accurate and efficient statistical operations. The application of the proposed modeling method to photovoltaic (PV) data yields quantiles for each system, presented in Figure 4, where the 98th percentile serves as an effective statistical clear sky model. Quantiles collapse to zero at night, with the spread between upper quantiles being narrower than that of lower quantiles, especially around noon. Each system exhibits distinct characteristics, with those physically near each other showing similar shaped quantiles. The paper also presents samples of the associated piecewise linear copula transforms in Figure 5, illustrating the time-aware copula transforms adaptation to both time of day and unique system characteristics. The AR model used has memory m equals 3, with coefficients indicating that the previous period plays a larger role in predicting the current values than the previous two values. The residuals of the AR model are fit to a smoothly varying periodic Gaussian distribution, as shown in Figure 6, with the top plot displaying small means, the middle plot showing varying standard deviations across systems and time of day, and the bottom plot illustrating correlations around 30% between selected pairs of residuals, with higher correlation for systems near each other. Finally, the paper discusses generating simulated data from the model by simulating data from the periodic Gaussian stochastic process and applying the inverse n online arities phi-1t, ito the entries of these samples. Figure 7 presents two simulations of fake data for comparison. The application of a novel probabilistic model to solar power forecasting, anomaly detection, and imputation is discussed. This model utilizes a multilinear tensor factorization approach to predict future solar power output based on historical data from multiple systems. It also allows for the computation of conditional marginal quantiles, which can be used for anomaly detection and imputation of missing values. The model's ability to adapt to changing weather conditions is demonstrated through examples of clear and partially cloudy days. Conditional marginal quantiles are computed for System 1 at 5 different times on these days, showing that the model correctly adjusts uncertainty bounds according to weather conditions. Predictions are accurate, as indicated by conditional median values. The model is also used for anomaly detection, identifying synthetic anomalies with a threshold of epsilon equals 0.01, along with 3 false positives likely due to unexpected cloud cover. Finally, the forecasting capabilities of the model are demonstrated by predicting the values of System 2 from 1315 onwards, using data from all systems up to 1300. The forecast, along with its conditional marginal 10th and 90th quantiles, is presented for both a clear day and a cloudy day, showcasing the model's versatility and effectiveness in solar power forecasting, anomaly detection, and imputation. The authors demonstrate the forecasting capabilities of their proposed model for photovoltaic systems through Figures 911. Figure 9 illustrates the marginal conditional quantiles for System 2 on April 1, 2017, with 6 artificial anomalies added, showcasing the predicted 10th, 50th, and 90th quantiles alongside the true power values. Figure 10 displays the forecast for System 2 on a clear day, April 9, 2017, and a cloudy day, April 6, 2017, generated from 1315 onwards, given values for all systems up through 1800. The cloudy day forecast exhibits wider uncertainty bands, yet remains reasonable. In Figure 11, the authors demonstrate joint forecasting using all systems, forecasting values of System 2 from 1315 onwards, using data from all systems up through 1300. 3 sampled forecasts from the full joint conditional distribution are shown, agreeing with the marginal forecasts, with generated instances falling within the 1090% confidence bands of the marginal forecasts. The forecasts capture the difference in behavior between clear and cloudy days, with the latter exhibiting more volatility. The authors summarize their novel approach to modeling and analyzing fleets of photovoltaic systems using a smooth periodic Gaussian Copula transform, highlighting its scalability to larger problems, with details forthcoming in a future paper. They acknowledge the support of the U.S. Department of Energy's Office of Energy Efficiency and Renewable Energy, as well as the AI Chip Center for Emerging Smart Systems. The paper presents a comprehensive list of 15 distinct deep learning architectures for image segmentation tasks, each tailored to address specific challenges in medical imaging. These architectures are categorized into three main groups: encoder-decoder models, U-net variants, and hybrid models. The encoder-decoder models, comprising 6 architectures, leverage the strengths of both convolutional neural networks, CNNs, and recurrent neural networks, RNNs, to capture spatial and temporal dependencies in medical images. The U-net variants, consisting of 5 architectures, build upon the classic U-net framework, introducing modifications such as attention mechanisms, dilated convolutions, and multi-scale feature fusion to enhance segmentation performance. The hybrid models, which include 4 architectures, combine the strengths of CNNs and transformers to capture long-range dependencies and contextual information in medical images. Notably, the paper introduces a novel hybrid architecture, dubbed the segmenter transformer, which achieves state-of-the-art performance on 3 benchmark datasets for medical image segmentation tasks. The authors conduct an exhaustive evaluation of these architectures on 5 benchmark datasets, encompassing various medical imaging modalities, including MRI, CT, and X-ray. The results demonstrate that the proposed segmenter transformer architecture outperforms existing state-of-the-art models, achieving a mean dice similarity coefficient of 0.923 and a mean IOU of 0.857. The study highlights the importance of architectural design choices and hyperparameter tuning for achieving optimal performance in medical image segmentation tasks. Furthermore, the authors identify avenues for future work, including the exploration of multimodal and multitask learning strategies to further improve segmentation accuracy and robustness.